Okay, in this video, we're going to talk about section 6.1, and it deals with matrix solutions to linear systems. And in this particular section, in this video, we're going to be writing augmented matrix for a linear system. We're going to be performing matrix row operations and use matrices and Gaussian elimination to solve systems. So to begin this particular section, we need to start off with some basic definitions. And one of them would be a matrix. And the plural for that would be matrices. A matrix is a rectangular array of numbers arranged in rows and columns. The numbers inside the brackets are called elements. So this is an example of what a matrix looks like. Okay, here we have a rectangular array, and it is in the form of brackets, and it's in rows and columns. So here there are two rows here, and as you can see, columns go up and down. There's 6 columns here. So the dimensions of that would be 2 rows by 6. So this is a 2 by 6 matrix because there are 2 rows, 6 columns. Okay. And each number that you see inside the brackets are called elements. So each number is an element. Next, we'll talk about what an augmented matrix is. An augmented matrix has a vertical bar separating the columns of the matrix into 2 groups. The coefficients of each variable are placed on the left side, on the left of the vertical line, and the constants are placed on to the right. If any variable is missing, its coefficient is going to be 0. So if you look at the left side, you see a system of linear equations, and on the right side is the augmented matrix for each system. So with 3x plus y plus 2z is equal to 31, and then x plus y plus 2z is equal to 19, and then x plus 3y plus 2z is equal to 25. Here, that can be converted into an augmented matrix. So in this case here, that first equation, 3x plus y plus 2z is equal to 31, we just write the numerical coefficients of 3, the coefficient of y is 1, and then for z it'll be 2. And then the 31 will be behind the vertical bar. Now I need to mention that the first column is your x coefficients, the second column is your y coefficients, the third column is the z coefficients. And then for the x plus y plus 2z is equal to 19, we can write down their numerical coefficients. For x, it's the understood 1. For y, it's 1. And for z, it's 2. The constant is 19. And then the last equation, x plus 3y plus 2z is equal to 25. Here, the coefficient of x is the 1. The coefficient of y is 3. The coefficient of z is 2, and then 25 goes here. So that vertical bar represents the equal sign for each equation. Now this other one, x plus 2y minus 5z equals negative 19, y plus 3z is equal to 9, and z is equal to 4. This is a case where if you have a missing variable, you have to compensate that with a 0 coefficient. So for the first equation, x plus 2y minus 5z is equal to negative 19. We do have an x, that coefficient there is 1. We do have a y term, the coefficient is 2. And for z, negative 5. Negative 19 goes behind the vertical bar. The next equation, y plus 3z is equal to 9. We're missing an x coefficient here, well, an x term here, so we put a 0 for that coefficient. For the y, it's the understood 1. For z, it's 3. And the 9 goes here, behind the vertical bar. And then finally, z is equal to 4. In this case here, we're missing an x and a y term. So for the missing x term, we put a 0 there, and for the missing y term, a 0 goes there. The z coefficient will be 1, and the constant term of 4 goes behind the vertical bar. So that's how we convert from a system of linear equations to an augmented matrix. Okay. Now, before we do anything, let's look at example 1 on the first page. We want to determine if 10, -7, 11, and this is what we call an ordered triple, because we have 3 numbers in the parentheses, an x, a y, and a z. We want to know that ordered triple is a solution to this system. X plus y plus z is equal to 14, x minus 2y minus z is equal to 13, and 2x minus y minus 2z is equal to 5. Okay. In this case, in that ordered triple, 10, -7, 11, that x is 10, the y is -7, and z is equal to 11. So what we got to do here is substitute x, y, and z into each one of those we have to substitute the x, the y, and the z with those values into each one of those equations to see if the left side does equal to the right side. So I'm going to start with the x plus y plus z is equal to 14. All right, so we substitute the x with the 10 plus the y, which is -7, plus z, which is 11. And that should equal to 14. Adding from left to right, 10 plus -7 would be 3. And if I add 3 plus 11, that does give me 14. So we know the ordered triple satisfies the first equation. But what about the second and the third equation? That ordered triple must satisfy all 3 equations, because that's to satisfy the entire system. In this case, so that second equation is x minus 2y minus z equals 13. So again, I'm going to substitute this x with the 10, then minus 2 times y is -7, minus z is 11. That should equal to 13. Okay. Bring down the 10. Minus 2 times -7 would be a plus 14. So I get 10 plus 14 minus 11. That should equal to 13. Add 10 and 14 together, you'll get 24. 24 minus 11 does give you 13. So we know the ordered triple satisfies the first and the second equation. But what about the third? Which is 2x minus y minus 2z equals 5. And here I want to find out if this ordered triple satisfies this third equation. Again, substitute the x with 10, so we get 2 times 10 minus the y, which is -7, minus 2 times z, which is 11. This should equal to 5. Now, if I do 2 times 10, that's 20. Minus a -7 would be +7. Minus 2 times 11, that's 22. And that should equal to 5. Now, 20 plus 7 is 27. 27 minus 22 does give us 5. So as you can see here, the left side and the right side are the same for all 3 equations in that system. So I can conclude that the ordered triple 10, -7, and 11 is the solution to the system. Okay. So that order triple 10, -7, and 11 does satisfy the system of linear equations as you see here. Okay. So now we can go ahead and start with example 2, writing the augmented matrix for this system of linear equations. Here we got 9x plus y plus 7z equals 4. 3x minus 8y minus z is equal to -7. And x minus 2y minus 2z equals -5. Okay, so to do that, we're going to need a bracket. That bracket inside will have the vertical bar. Okay, that vertical bar represents your equal sign. And if you want to, this is not necessary. The first column would be your x coefficients. The second column is your y coefficients. The third column is the coefficient of z. This last column behind the vertical bar represents the constant terms. Okay. Now again, if there are any missing coefficients, we compensate those with a 0 as its coefficient. So like let's start off with the first equation. 9x plus y plus 7z is equal to 4. We just write down the numerical coefficients there. For the x is 9. For the y is the understood 1. For the z is 7. And the 4 goes behind the vertical bar. And then for the second line, 3x minus 8y minus z is equal to -7. Here the coefficient of x is 3. The coefficient of y is -8. The coefficient of z, -1. And -7 as your constant term. And then you got x minus 2y minus 2z is equal to -5. Okay, we write there its numerical coefficients. For the x is the understood 1. For the y is -2. For the z is also -2. And then the constant term, -5. Okay, and that's all there is to it. All you have to do there is just write the augmented matrix for this system of linear equations. Okay, here's another example. This is example 3. You're going to write the augmented matrix for the system of linear equations. The augmented matrix for this system of linear equations. In this case, we got x minus y plus 8z is equal to 5. And then y minus 12z is equal to -11. And z is equal to 4. Okay, so we start off with a bracket with a vertical bar. Now, if you want to, you can do this to help you out. The x is the first column. Your x coefficients will be in the first column. The y coefficients in the second column. The z coefficients in the third column. The constant terms go behind the vertical bar. And keep in mind that vertical bar represents the equal sign. Okay. So for the first equation, x minus y plus 8z equals to 5. Okay, let's write the numerical coefficients for that. For the x is the understood 1. For the y, the -1, because of the minus sign in front. For the z, the coefficient there is 8. The constant term is your 5. And then next we got y minus 12z is equal to negative 11. Notice in that equation there is no x term. So that means in this column for my x's, I have to put a 0 there. For the y, it's the understood 1. And for the z, it's negative 12. And the negative 11, that's the constant term that goes behind the vertical bar. And finally, the z equal 4. Notice that there is no x term, nor is there a y term. So, in the x column, I need to put a 0 coefficient there for the x, and in the y, I need to put a 0 coefficient for that. Now for the z, it's the understood 1 for its coefficient. The constant term is 4. Okay, so this is the augmented matrix for this system of linear equations. 1, negative 1, 8, 5, 0, 1, negative 2, 12, negative 11, 0, 0, 1, 4. Okay. Now, example 4 is this. You're going to write the system of linear equations represented by the augmented matrix. So here we're going to be going backwards. Here we got the augmented matrix. We want to know what the system of linear equations that is represented by that augmented matrix. And of course, if this helps, the first column is the coefficient of x, the second column is the coefficient of y, the third column is the coefficient of z, the constant term is behind the vertical bar. And of course, in a system, we're going to need a brace, a left brace here. And then we're going to read across to write this as a linear equation. So for 4, 0, 3, and negative 17, that 4 is the coefficient of x. So that's 4x. And if you have a 0 here, either for x, y, or z, we don't necessarily need to write it down. Because here, 0, that's the coefficient of y. So we don't need to write 0, y. But we do have a 3 here. That's the coefficient for the z. So here, this will be plus 3z. And that vertical bar is the equal to, and then the constant term, negative 17. So that first row represents 4x plus 3z is equal to negative 17. Now, for the second row, notice this 0 is the coefficient of x, so we don't need to write 0x. But for the 1, that's the coefficient of y. So you can write 1y or just y, and then negative 6, that's the coefficient of z. So I'll write that as a minus 6z. And then that's equal to the constant term, 14. And then for the last row, 9, 7, 0, and 2, that 9 is the coefficient of x. So this will be 9x. This 7 is the coefficient of y. So this will be plus 7y. That 0 is the coefficient of z. That will be 0z, but we're not going to write that. That will be equal to 2. So this is what the system of linear equations look like from that augmented matrix. 4x plus 3z equals negative 17. Y minus 6z equals 14. 9x plus 7y is equal to 2. So that's how you convert from a augmented matrix to a system of linear equations. All right, next we'll talk about this right here. One goal in solving a system of linear equations in 3 variables using matrices is to produce a matrix with ones along the ones down the diagonal from the upper left to the lower right on the left side of the vertical bar, and that's called the main diagonal, and zeros below the ones. So in general, the matrix will be of this form right here, as you can see. And I'm going to highlight the main diagonal. That's this right here. From the upper left to the lower right. That would be the main diagonal. And you're going to want zeros underneath that main diagonal. Underneath the ones. Okay. That's what we're going to be doing here in this particular section. And of course, A through F, that's these numbers up here, those represent real numbers. The third row of this matrix gives us the value of one variable. The other variables can then be found by using what they call back substitution. So, usually in this case, this would be z equal to something. And then you'll substitute z into the value of z in the second equation to get y. And then you'll substitute the y and the z in the first equation to get your x value. That's what we mean by back substitution. Okay. Now we're going to be doing this by using a concept called matrix row operations. And it's this. A matrix with ones down the main diagonal and zeros below the ones is said to be in row echelon form. Here we use row operations on the augmented matrix. And in this box, this is the following row operations. The following row operations produce matrices that represent systems with the same solution set. Okay. Number one is this. Two rows of a matrix may be interchanged. That means you can swap rows. Number two, the elements of any row may be multiplied by a non-zero number, positive or negative. And number three, the elements in any row may be multiplied by a non-zero number, and then those products may be added to the corresponding elements in any other row. Okay. And here two matrices are row equivalent if one can be obtained from the other by a sequence of row operations. Okay, so symbolically, each row operation can be expressed as follows. Number one, you can interchange the elements in the ith row and the jth row. That would be row I can be interchanged with row j. And then number two, multiply each element in the ith row by some constant k. So here you can have k times some row I. And then number three, I add k times the element in row I to the corresponding elements in row j. So it'll be k times row I plus row j, as you can see. Okay, so let's look at some examples of this, of how to do matrix row operations. Okay, take a look at example 5 on the next page. It says here, use the matrix below and perform each indicated row operation. So here we got this matrix, which is 4, 12, negative 20, and 8, 1, 6, negative 3, 7, negative 3, negative 2, 1, negative 9. So here we're going to use that matrix to perform each indicated row operation, like in part A. We're going to do this. R1 and R2. Now those arrows means to interchange those rows. So we're going to interchange row 1 and row 2. And I'll go ahead and rewrite this. 4, 1, negative 3. I'm just writing this by column. 12, 6, negative 2, negative 20, negative 3, 1, and then 8, 7, negative 9. Now, what we want to do here is interchange row 1 and row 2. And what that means here is this. The elements in row 1 will go to the elements in row 2, and what's in row 2 will go to row 1. So that means row 2 will become the new row 1. So this is going to be 1, 6, negative 3, and 7 in the first row. And then row 1 becomes row 2. So this will be 4, 12, negative 20, and 8. Now the third row, I'm going to copy that over. That's going to stay the same. So this is our new matrix after interchanging or swapping row 1 and row 2. Okay. So that's going to be, that is part A. Part B is this. They want you to take 1/4 of row 1. So we're looking at the original matrix that we started off with. Not this one. We're looking at this one right here. So I'm going to copy that again. So this is 4, 1, negative 3, 12, 6, negative 2, negative 20, negative 3, 1, and then 8, 7, negative 9. And we want to take 1/4 of row 1 to get this. So all we have to do there is take each element in row 1 and multiply it by 1/4. Or you can think of that as dividing by 4. So if I take 1/4 of 4, that's like 1/4 times 4. That's going to give me 1. Or 4 divided by 4 will be 1. You can think of that if you want. And then 12 times 1/4. Or 12 divided by 4. That would be 3. And then negative 20 times 1/4. Or negative 20 divided by 4 is negative 5. And then finally 8 times 1/4. Or 8 divided by 4. That will be 2. And then the other row 2 will remain the same, so I can copy that over. And row 3 remains the same. So I'll copy that over. So that is what your matrix looks like after doing 1/4 times each element in row 1. Okay, so that's part B. Now part C is this. I'm going to take 3 times the element, each element in row 2, and add that to row 3. Three times the element in each element in row 2 and add it to row 3. So let me copy the original matrix here. Let's see. 4, 1, negative 3. I'm doing this by column. 12, 6, and negative 2. Then negative 20, negative 3, and 1. And then 8, 7, negative 9. So what's going to change is row 3. Row 1 and row 2 are going to remain the same. It's row 3 that's going to change. And that's going to be changing by doing 3 times the element in row 1 row 2 plus the element in each element in row 3. So here's what we're going to get. The first 2 rows are going to remain the same. So I'll copy those over. 1, 6, -3, and 7. So here's what we're going to do here. I need to move this up a bit. I'm going to take 3 times each individual element in row 2 and add that to each element in row 3. Okay, so here's what we got. 3 times row 2. So that means I'm going to do 3 times 1, and I'll write this down at the bottom. 3 times 1, and then I'm going to add that to that element, the corresponding element in row 3, which is -3. So in this case, 3 times 1 would be 3. 3 plus the -3 is 0. So that 0 is going to go here. And then 3 times the next element in row 2, that's 6. So it'd be 3 times 6 plus its corresponding element in row 3, -2. So 3 times 6 is 18. 18 plus -2 is 16. That's going to go here. And then 3 times the element in row 3. 3 times this -3. And then plus the corresponding element, which in row 3 is 1. So 3 times a -3 is -9. -9 plus 1, that's -8. So that -8 goes here. And then finally, I'll do 3 times row 2. That's right here, row 2. That's 7. So it'll be 3 times 7 plus the element in row 3, -9. So 3 times 7 is 21. 21 plus -9 is 12. So that 12 goes here. Okay. So that's how we do matrix row operations here. Okay. Now the idea of that is going to be very, very useful when we solve a system of equations using what they call the Gaussian elimination. Okay. That's this right here. Because the idea is to get get ones along the main diagonal and zeros underneath those ones. And then you can do back substitution. So here the first step would be to write the augmented matrix for that equation or for that system of equations. Okay. Now, number 2, you're going to use matrix row operations to simplify the matrix in a row equivalent matrix in row echelon form with ones down the main diagonal from the upper left to the lower right and zeros below the ones. So you want to start off with the 1 in the upper left-hand corner and do whatever matrix operations you have to in order to get zeros underneath the ones, underneath that 1 in the first column. And then work on trying to get a 1 in the middle row, middle column. And keep doing that until you get a 0 underneath the 1. And then finally, you want to get a 1 in the third column. So notice that the ones are going to be in a form of a diagonal. And then you're going to write the system of linear equations corresponding to the matrix in step 2 and use the back substitution approach to find the system's solution. Okay? All right, so get ready for what I'm about to do here on the next page, which is example 6. Here it is. We are going to use matrices to solve this system, and we are going to be using the Gaussian elimination. In other words, we're going to try to get ones along the main diagonal and zeros underneath the ones, and then do what they call back substitution. So here you got 2x plus y plus 2z is equal to 18. And x minus y plus 2z is equal to 9. And then x plus 2y minus z is equal to 6. Okay. So the first step, we need to write that as an augmented matrix. So let's start by writing in our bracket that first row, 2x plus 2y plus 2z is equal to 18. The x has the coefficient of 2. This y has the coefficient of 1. The z has the coefficient of 2. The constant term, 18. That's the first row. The second row, x minus y plus 2z is equal to 9. That x has the coefficient of 1. This y has the coefficient of negative 1. The z has the coefficient of 2. And then the 9 is the constant term. And then the final equation, x plus 2y minus z is equal to 6. The coefficient of x, again, that's 1. For the y, its coefficient is 2. The z is negative 1 for its coefficient. And 6 is your constant term. Okay. And now we're going to use matrix row operations to find out what x, y, and z are going to be equal to. Now I need to mention that there is no set way of doing these problems. You just have to kind of think about what you have and try to use those matrix row operations to the best of your ability. Okay? So like in this, so to start off, I want a 1 in the upper left-hand corner. So I need a 1 up here. I got 1s underneath it. So what I'm going to do here is this. I'm going to interchange rows here. I'm going to interchange row 1 and row 2. That way I can have a 1 on top. Because that's the objective there, is to get 1s along the main diagonal here. So if I interchange the first 2 rows, this is what I will have. Row 1 will become, this row 2 becomes row 1. So it'll be 1, negative 1, 2, and 9. Then the second row will be what was row 1, 2, 1, 2, 18. The third row remains the same. 1, 2, negative 1, 6. So there you have it. So I have 1 up here. Now, I want to get zeros underneath that 1. I want that 2 to be a 0 and this 1 to be a 0. And we can do this in, now we don't have to do each row operation individual. We can do 2 of them at the same time. Okay? So, notice I got a 2 here. If I want to make that 2 a 0, this is what I need to do. It's a positive 2, so I need to do the opposite of 2, which is negative 2. So I got to do negative 2 times each element in row 1. Negative 2 times row 1. Then I'm going to add it to row 2. Now I'm going to also do this here. Get a 0 down here as well, because I have a 1, I need a 0 here and a 0 here. Well, I can do this as a positive 1, so it would be negative 1 times row 1 plus row 3. Because I'm going to take each element in row 1, take the opposite of it, and then add that to each element in row 3. So when I do that, I'm going to have to continue this on the next line here. The first row remains the same, the 1, negative 1, 2, and 9. It's row 2 and row 3 that's going to change. And I'm going to go ahead and write this out for you so that way you can see how this is done. Negative 2 times row 1. That's this. Here's row 1. And I'm going to take negative 2 times that and then add it to row 2. So that means negative 2 times row 1, which is 1, plus the corresponding element in row 2, which is 2. So I got negative 2 times 1 plus 2. Well, negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. So that 0 goes here, which is what I want. And then I got to do the same thing and add it to these corresponding elements here, like the negative 1. I got to do negative 2 times negative 1 and then add that to the 1. Well, negative 2 times negative 1 is 2. 2 plus 1 is 3. So I'm going to put a 3 here. And then negative 2 times row 1, go into this one right here. Negative 2 times that 2 plus the corresponding element, which is 2. That's in row 2. So here, negative 2 times negative 2, well, negative 2 times 2 is negative 4. Negative 4 plus 2 would be negative 2. So that negative 2 goes here. And then negative 2 times the first row, that's the 9. Negative 2 times 9 plus what's in row 2, 18. Negative 2 times 9 is negative 18. Negative 18 plus 18 is 0. So that 0 goes here. Okay. And now, I'm going to take the opposite of row 1 and add it to row 3. And I'm going to do this way up here. So the opposite, or negative, what's in row 1, that's 1, plus what's in the corresponding element in row 1. So negative 1 plus 1 is 0. Now in this case here, the opposite of what's in row 1, that's a negative of negative 1 plus the corresponding element in row 3. That's 2. Well, the opposite of negative 1 is 1. 1 plus 2 is 3. So I need to put the 0 here and the 3 here. And then, in this case here, the opposite of row 1, that's a 2. The opposite of 2 plus the corresponding element in row 3, negative 1. So negative 2 plus negative 1 is negative 3. That will go here. And then finally, the opposite of row 1, that's the opposite of 9. And I'm sorry that I'm running out of space here. That's negative 9 plus the corresponding element in row 3. That's 6. So negative 9 plus 6 is negative 3. So notice, this is what I have. Okay. All right, next, notice I got a 0 and then 3's down here. 3, negative 3, negative 3. I'm going to make that a 1 because they're all multiples of 3. What I'm going to do here is take 1/3 of what's in row 3. One-third of row 3. Now the first two rows are going to remain the same. The one, negative 1, 2, and 9. And then 0, 3, negative 2, 0. Now, 1/3 of each element in row 3. So 1/3 of 0 is 0. 1/3 of 3, or 3 divided by 3, is going to be 1. 1/3 of a negative 3, negative 1. And the same thing, 1/3 of negative 3, again, negative 1. Okay. So here, I got a 1 here with zeros underneath it. So now I want a 1 right here in this middle column, middle row. But notice I got a 1 down here as well with a 0 in front. So I can go ahead and interchange row 2 and row 3. That's what I'll do, interchange row 1 and row 3. That way I'll have a 1 in the middle row, middle column. So here, the first row remains the same. 1, negative 1, 2, and 9. But the second row will be replaced with what's in the third row. So this third row will become row 2. So put the 0, negative 1, 0, 1, negative 1, and negative 1 there. The 0, 3, negative 2, 0 will become row 3. Okay. Now the last thing I need to do here, I got a 1 here, but I need a 0 underneath that 1. Well, let's think about this. If I do, and it's a positive 3, so I need to make that negative 3 times what's in row 2, and I'm going to add that to the corresponding elements in row 3. So this is what I'll have. The first row stays the same. The second row stays the same. The third row is going to change. And it will be this. Taking negative 3 times what's in for each element in row 2. So starting with the negative 3 times the element in row 2, which is 0. Add that to the corresponding element in row 3. That's 0. Well, negative 3 times 0 is 0. 0 plus 0 is 0. So we'll put the 0 there. And then next will be negative 3 times this element in row 2, which is 1. Add that to the corresponding element, which is 3. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. And then next will be negative 3 times what's in row 2. So it'll be negative 3 times, in this case, negative 1, plus the corresponding element in row 3, negative 2. Negative 3 times negative 1 is 3. 3 plus negative 2 is 1. And then finally, negative 3 times what's in row 2. That's going to be negative 1 plus the 0, that corresponding element. Negative 3 times a negative 1 would be 3. 3 plus 0 is 3. That goes here. And I am done with that problem because notice I have 1s along the main diagonal and zeros underneath them. Okay. So what I'm going to do here is write this as a linear equation, as a system of linear equations, and then I'm going to do back substitution. So that first row represents this: 1x, or just x, minus 1y, or just minus y, and then plus 2z is equal to 9. Keep in mind, the first column is your x term, x coefficients. The second column is the y coefficients. The third column is the z coefficients. The last column after the vertical bar represents the constants. The vertical bar is your equal sign. Now the second row, this is 1x, or just x, minus 1y, or just y, so it'll be x minus y. No, take that back. That's 0x, so I don't need to write that. But this 1 is the coefficient of y, so it'll be y minus 1z, or just z, equals negative 1. Now the last row, 0x, 0y, 1z, or just z, equals to 3. So I know what z is equal to. Z is equal to 3. Now here's where the back substitution comes in. Since z is equal to 3, I can substitute the 3 in for z in this second equation to find out what y is. So here, I'm going to have y minus 3 equal negative 1. And then to solve for y, add 3 to both sides. That would give you y is equal to 2. And now z is 3 and y is equal to 2. I'm going to find out what x is. Using the first equation, substitute the y with the 2 and the z with 3. So here I'm going to have x minus y is 2 plus 2 times z, which is 3. That's equal to 9. So now x minus 2, then plus 2 times 3 is 6. That's equal to 9. Now, minus 2 plus 6 is going to be 4, so it'll be x plus 4 is equal to 9. And then we're going to subtract 4 on both sides. That means x is equal to 5. Okay, so we have our x, our y, and our z. So the solution to that ordered triple, or to that system of linear equations, is the ordered triple 5, 2, and 3. Okay. So pretty much we had to go through all of this to get to that one answer. And I'm going to leave the check up to you, so you can check by replacing the x and the y and the z in the original equations, in the original system. And that should check out. Okay. There's a spoiler alert. Look on the last page. What I just did can be done on the TI-83 or 84 Plus calculator. And I say 83, but the 84 works as well. So most graphing utilities can be used to convert a matrix into reduced row echelon form. And what's reduced row echelon form is that you must obtain ones along the main diagonal and zeros above and below each of the ones. And when you do that, you will get the values of x, y, and z. And on that last page, you'll see that procedure here. But since it is a spoiler alert, I'll go ahead and show you how to do this on the calculator. Okay, here we go. All right, let's clear this out. Now, the first step is to access the matrix menu by pressing the second key, and X to the negative 1. So I'm going to press this button, which is the second key, and then X to the negative 1. That's underneath the math button. Now, the second step is to move the cursor using your right arrow key to get to the edit menu, because we're typing in a new matrix here. Okay, and I'm going to select number 1 because it's going to be matrix A. Now, you're going to get this. There are two numbers here. The first number that's blinking over it is the number of rows. The second number after the X is the number of columns. If you look at this matrix right here, there are 3 rows, and actually 1, 2, 3, 4 columns. You have to know what the dimensions are because you have to tell it what dimensions you want. So the first number will be a 3, so I type in the 3 for 3 rows and then hit enter. And I want 4 columns, so I need to type in number 4 for 4 columns, and it will give me 3 rows, 4 columns. Now you might have dots on the far end, and it depends upon the type of window you have, because there's more to it, because your window can only fit so much. Your calculator can only fit so much in that window that you have. Now, the next thing we'll do here is type each number row by row. That's step number 4. Pressing enter after each number. So the first row is 2, 1, 2, and 18. So I'm going to type in the number 2 and then enter. Then 1, enter. 2, enter. And 18, and then enter. And then the next row, because what happens when you press enter, it'll take you to the next row where you enter the next row of numbers, pressing enter after each time. The next row is 1, negative 1, 2, and 9, so it'll be 1, and then negative 1. Make sure that you press the negative key, which is at the very bottom of your calculator, and then type 2, enter, and then 9, enter. And it'll take you to the third row where you have to type in 1, 2, negative 1, and 6. So it'll be 1, enter, 2, enter, negative 1, enter, and then 6, you have to press enter. Even after the very last number, you have to press enter. Now, the next step is to get out of the matrix menu by pressing second mode. So here's second and then mode. Second and then mode will take you back to the home screen. And then next is to get the reduced row echelon form. You're going to press second and then X to the negative 1, which is underneath the math key. You're going to move the cursor to the math menu. And you're going to use your down arrow key to find a menu item that says RREF, which is this. That is reduced row echelon form. Do not select REF. That's only reduced echelon form. Okay? Don't pick that one. You want RREF for reduced row echelon form. And then press enter. It'll put RREF with the left parentheses. Now I want to pull up that matrix that I saved in A. So here's what I'm going to do. The next step is going to be second and X to the negative 1 for the matrix menu. Second X to the negative 1. And under the names, I stored it in A, so I'm going to select A by selecting number 1. And then it's going to pull that up with RREF and then the A in the bracket. Now you can close the parentheses if you want to, and then finally press enter. Now, this is going to give you the reduced row echelon form. Now, if you look at the numbers that are in the final column on the far right, that tells you the values of x, y, and z. So that means your x is going to be 5, y is equal to 2, z is equal to 3, which is exactly what we came up with in that particular, when we did the Gaussian elimination. And by the way, with zeros on the top of the ones, above and below the ones, we call that Gauss-Jordan elimination. And what we did by hand was the Gaussian elimination. Okay, so that completes this video on section 6.1, dealing with matrix solutions to linear systems. And that homework should be available for you to complete on my math lab. And feel free to email me or well, just email me if you have any questions or concerns about the homework. And watch this video as much as you need to.